Hello engineers, welcome to the new video of the course, and in this particular video we are going to solve a numerical based on monostable multivibrator mode. So if you could remember, in the previous session we saw the theoretical part of the monostable multivibrator. Over there we saw its internal circuit diagram, and based upon that we saw that how exactly things work internally in 555 timer IC in monostable mode. And then at the end we deduced this kind of waveform graph, if you could remember. Okay, and then we also deduce the equation for t on period. Okay, that means the quasi-stable state which is present in the monostable multivibrator mode. That means this t on period, right, which is our output waveform. So now we just focus over here onto this particular question. So design a circuit such that LED remains on for around 1.1 millisecond. So this is the this is our t on. That means it is my quasi-stable state. Let me just write over here. This is my t on, that is my quasi-stable state. Quasi-stable state. So my quasi-stable state is of around 1.1 millisecond. Okay, and it should remain on only if the input switch is pressed. Okay, and the hint is obviously to use a monostable multivibrator mode. So you see this is my switch. Okay, so whenever I close this particular switch, right, whenever I close this particular switch, that means what, I'm pressing this particular switch at that particular time, or from that particular time, the moment I press the switch, this LED, so this LED, it should remain on. It should be in on condition, or it should remain on for how much minutes or for how much millisecond? For around 1.1 millisecond. Okay, for around 1.1 millisecond it should remain on. So this is how we have to design a circuit. Okay, and we all know that we have already learned monostable multivibrator mode. So how exactly we are going to do so? So it's pretty simple. This is my circuit of 555 timer IC. So obviously this is my third pin, that is my Vout. This is my reset pin, discharge pin, threshold pin, and obviously we need to connect discharge and threshold pin, right? We need to just short circuit these two pins, and then we need to connect it to the timer block, which is nothing but RA and C, right? From here we are going to give the input, that is my triggering pin. Okay, so this is the input, this is the ground terminal, that is pin number 1. Pin number 5 is control pin. As of now, it does not have any usage, so we connect it to ground with the help of the capacitor just to reduce any noise. Okay, so this capacitor value, it should be very less. Okay, generally it is in 0.01 microfarad, so that obviously the frequency of noise is quite high, so that for that we select the capacitor of that particular value, so that it completely nullify the noise. So what we need to do now, like how to proceed further. Okay, because we want a timed t on. Okay, we want t on, that is my quasi-stable state. It should be of around 1.1 millisecond. So how should we proceed further? Well, if you could remember, we derived one equation for t on, right? That what was that equation? If you could remember, it was 1.1 into R into C, right? So that means what, 1.1 into this RA times of C. Okay, I hope you are able to understand this. So we need to find out the value for RA and C. Okay, that means C. Yeah, over here you see this particular equation RA. Over here it should be RA. Let me just erase everything over here and let me just write it once again. So what we know is my T on is equivalent to RA times of C. Okay, so what is my RA and what is my C? This is what we don't know. Sorry, my bad. It should be 1.1 times of RA and C. So T on is equal to 1.1 times of RA into C. So what is my RA and C? That we don't know. So basically, in this kind of thing, or in this kind of scenario, we need to assume one of the values. Okay, we need to assume one of the values, and then we will easily get the other value. I know most of you guys may think that why exactly we are assuming one value. Okay, see, this becomes pretty easier to design this kind of circuits, right? Whenever we deal with capacitor and resistors, okay, this kind of circuit, so we need to assume the values of either one of them, right? But in most of the cases we assume the value for resistors. Okay, now I know most of you guys may think that then what value should we select? Should we take RA as 1k or 10 kilo ohm or 100 kilo ohms or maybe 0.1 kilo ohm? We don't know, like what value should we select, because there are different designers out there in the market. They will select different values of this RA. So what value should we go with? Well, for that you need to refer this particular graph. Let me just show it to you. If you could remember, when we just saw the data sheet, over there I told you that we will be focusing upon this particular graph in future. And this particular graph, basically this PDF is of Texas Instrument, and yeah, on page number 10, you see on page number 10 over here, you will get this graph over here. Okay, so the graph is between the capacitance. Let me just see if I can zoom out this particular graph. One sec. Over here I'm not getting a sign for zooming out. Let me just do it with my mouse only, if at all I can do that. Yes, of course I can do that. Yeah, so now you just focus on this particular graph. So the graph, you see over here, it is plot between capacitance. So on x-axis we have capacitance in microfarad, okay, and on y-axis we have this output pulse duration, right? Output pulse duration, okay, output pulse duration in seconds, right? Now we just focus over here on our on the question. The question is, we want the one sec. Yeah, we want T on for around 1.1 millisecond. So I'll roughly take it as 1 millisecond. Okay, let's assume that our T on is 1 millisecond. T on is 1 millisecond. Okay, so in this graph we have to find 1 millisecond. Okay, that means on y-axis we have to find 1 millisecond, because you see the output pulse duration, right? So 1 millisecond can also be written as 10 raised to minus of 3 seconds, right? So where can you see this particular value, that is 10 raised to minus of 3 millisecond, I mean 10 raised to minus of 3 second? Of course you can see it over here, right? So this is 10 raised to minus 5 minus 4 minus 3. So over here it is. Okay, over here it is. And let's say I go with 10 kilo ohm of resistor. Okay, 10 kilo ohm of resistor. If you want, you can go with 100k as well. That is absolutely fine. Okay, you can go with this particular value as well. In fact, you can go with 1k as well, right? It's up to you, but I'll prefer 10k. Okay, I'll prefer 10k. Okay, so I'll just erase this and I'll just highlight this particular point, that let's say my RA is 10k. This is, let me erase this as well so that it should look proper. Yeah, this is my 1 millisecond roughly. It is 1.1 millisecond, right? But I'll consider it as 1 millisecond. So let's say if I plot this particular thing over here, so that will be roughly around, I mean close to 0.1 microfarad, right? 0.1 microfarad. So that means what? That means if I assume the value of RA as 10k, okay, and if my width of pulse, I mean the T on time, if it is of 1 millisecond roughly, okay, not exactly roughly, if it is of 1 millisecond, then the capacitance value, it will be around 0.1 microfarad. Okay, so this is how we actually proceed further whenever we deal with this kind of circuit. Okay, I know most of the guys, maybe if you had watched this kind of videos on YouTube or maybe some other platforms, they directly assume, let's say RA as 10k, and then they find the value of capacitance. So that value is, I mean, it is exactly this one only. That means it matches, it will generally match with this value only, that is 0.1 microfarad. But they don't, I mean, they will not tell you like how exactly we got this particular value. It is present in the data sheet. So instead of doing this particular calculation, instead of doing this particular calculation, you can avoid this particular calculation and you can directly assume the value for RA and C. Okay, don't worry, I'll show you that as well, so that you should not get confused. Okay, so I really hope now you are able to understand this, that from where we are getting these particular values and why exactly we are assuming the values for RA and C whenever we are dealing with this kind of time delay circuit based on capacitor. Okay, sorry. So I really hope that you understood this particular part. Okay, now let's move on to our numerical and let's see. So as I had mentioned that I'll assume RA as 10k. Let's assume that, sorry, my RA is 10 kilo ohm, 10k. So what will be the capacitance? So a capacitor value. So T on is 1.1, right, which is 1.1 millisecond to be precise. Yeah, 1.1 millisecond. Okay, so 1.1 millisecond is 10 raised to minus of 3 second, is equivalent to 1.1 into RA. I have assumed it as 10 into kilo ohm, means 10 raised to 3, right? And then I have capacitor, that is C. Sorry. So 1.1 and this gets cancelled. We have 10 raised to 3 and we have 10 over here, so that becomes 10 raised to 4. Okay, that comes down. So this becomes, it will look something like this. 10 raised to minus of 3 divided by, in fact, instead of I was just saying, I'll just write over here 10 raised to, so that will be around 10 raised to minus of 7 only, but still for your understanding purpose, this will be 10 raised to 4, right? 10 raised to 4, this is my C. Okay, so this 4 comes up and that becomes 10 raised to minus of 4. So eventually we end up getting value as value of capacitor as C is equivalent to 10 raised to minus of 3 times of 10 raised to minus of 4, right? 10 raised to minus of 4, so that is nothing but 10 raised to minus of 7, right? Or else I can also write this particular value as mentioned in the datasheet, that my C is equivalent to, what I'll do, I'll just take 10 raised to minus of 1 times of 10 raised to minus of 6, right? I hope you know this basic mathematics, right? So that becomes 0.1 into 10 raised to minus of 6, which is nothing but 0.1 microfarad. And if you could remember in the datasheet as well, I clearly mentioned that the value, it might lie somewhere close to this particular value. So instead of doing all of this mathematical work, you can directly jump onto those particular values. That is also absolutely fine. Okay, and I really hope now your concept is clear, that from where we got all of these particular values. And most of the YouTubers and all of these guys who explain you the concepts over there, they don't explain you this particular thing. Okay, they don't refer to the data sheet. Okay, like why we are assuming 10 raised to 3, why not we are going with 1 mega ohms, why not we are going with 100 kilo ohms, right? Okay, what if we go with this particular values, what value we can expect for the capacitor at that particular time? So all of this question, it is present in the data sheet itself, and I had explained you this particular part. Okay, so you can work around with other values and you can find the T on time. I hope your values matches with this particular values. I hope this particular part is crystal clear. So now let's proceed further. Now what we are going to do, we are going to simulate this particular circuit and then we'll check the waveforms. Okay, so let me just run this particular circuit. Go again over here and I'll just click over here and then I'll plot my output waveform. So yeah, I'll keep it as red. I don't want blue color. Yeah, you see the output waveform. So you see over here now my output waveform exactly starts at 1 millisecond. Why? Because exactly at 1 millisecond I'm triggering this particular event. I'm providing the triggering voltage exactly at 1 millisecond, right? The moment I provide triggering voltage, okay, the capacitor starts charging, and from that very point I'm able to see the output waveform, right? Okay, till what point? Till 2.1 millisecond, right? See this particular point till 2.1 millisecond, right? So this point should be 2.1 millisecond. So this is 2.1 millisecond, this is 1 millisecond, right? And the time interval between both of them is my T on time, this we want, which is 1.1 millisecond, right? Sorry, 1.1 millisecond. Okay, I hope this particular part is absolutely clear. Okay, we'll just verify this as well, so don't worry about that. So one second, let me move this cursor somewhere over here. Yeah, 1 millisecond, you see at 1 millisecond, and let me just move the second cursor somewhere over here. That should be roughly around 2.1. Yeah, you see 2.1 millisecond, right? And you see the difference between both of them, it is 1.1 millisecond, and this is what we wanted, right? That means what? The question was to achieve a 1.1 millisecond, the question was to keep LED on for 1.1 millisecond whenever I press the switch. And what I mean when I press the switch, that means whenever I provide the triggering pulse, right? So the moment I provide the triggering pulse, because obviously you want to, you press the switch, right? Let's say instead of switch, it's a push button, right? Just press the push button, right? So what is going to happen? This particular triggering pulse is generated, and due to which all of this particular events starts happening, like the capacitor starts charging, and as the capacitor charges, you will get the output waveform, something like this. I hope this particular part is crystal clear. So what I'll do, I'll just keep this transient as at maybe let's say stop time, I'll keep it as, let me check, I'll keep it as 6 millisecond. Okay, because any which ways this part is wasted, so why to show that, I'll click on OK and I'll click on run. Yeah, so if you want you can just take a screenshot of this particular circuit and all, and now you can clearly look at this particular circuit, sorry, this particular waveform. It is visible, right? So what we can see over here, okay, we have completed the numerical part, that is fine, that is absolutely fine. But as an engineer, what can you guess? Okay, just by looking at the waveform. It's my request to you all guys that you please pause this video and try to think in your mind that what sir is actually trying to tell us. Just pause this video and try to think. Alright, I believe that you all guys have tried your best to think upon it, upon the waveform. Okay, what all things you observe over here? Okay, the most important observation is exactly at 1 millisecond I press the trigger. Okay, the capacitor starts charging, and exactly at 1 millisecond I'm able to get the output. That means what? The 555 timer IC is highly responsive. Okay, so you see at 1 millisecond, this is what I am telling you. You have to observe, right? You have to observe the things. 1 millisecond I'm pressing the triggering, I'm triggering the event, that means I'm giving the triggering pulse. At 1 millisecond the capacitor starts charging, that is absolutely fine. But the most important thing is that exactly at 1 millisecond I'm getting the output, exactly at 1 millisecond. That means what? If this is my system, right? If this is my system, I'm giving some certain input at 1 millisecond, exactly at 1 millisecond I'm getting the output as well. Okay, I'm getting the output as well. That means what? This particular system is highly responsive, right? It takes very less time or negligible time to give the output. Okay, if you provide certain input, within no time it will provide you the output. This is what we can see, and this is very important. So 555 timer IC is very responsive circuit. So this is what we saw, and since it is so responsive, that's why we use it when we want precise time delay. Okay, I hope you are able to understand this. Okay, I hope you are able to understand this, and this is what you should observe as an engineer, right? You always take time to observe. Okay, so I really hope that you understood each and everything that we discussed in the monostable mode. Okay, you also understood the circuit connection, you also understood its working, you also understood like how to plot waveforms, you understood this particular part, which I know I took some time to explain you this particular part, but I know most of the students, they get confused at this particular part, at this particular in this particular simulation, and I really don't want you all guys to get confused over here, like what value should I put, whether I put 5, 3 and all, etc, right? And at the end we saw this particular waveform, right? I explained each and every part in detailed way. But still, if you have any doubts, if you are facing any difficulties anywhere, it's my request to you all guys that you please ask those particular doubts in the communication section, and I will be happy to help you out there. So thank you for listening patiently. I'm ending this video over here. Thank you.